Welcome back to Honors Calculus. In this video, we're going to continue our discussion on the coordinate plane with some ideas on function notation. A function, you're probably already familiar, is a special kind of equation in two variables that has some nice properties on specifically the behavior with respect to the y-axis. So let's just dive in. Let me get my head out of the way here and take a look at a couple of ideas. A function is a rule relating, that doesn't look like the word relating. A function is a rule relating each element of one set called the domain to exactly one element of a second set called the codomain. This definition might look a little bit strange to you at first because normally when you define a function in an algebra class, instead of looking at the codomain, you look at the range. There is an important but subtle distinction between the idea of a codomain and the idea of a range. The codomain is the target set, and the range is the part of the target set that actually gets used. The range of a function is a subset of the codomain, which contains elements that are used by the function. Or it's the set of all elements for which there is an element in the domain where the function points that element to the particular element in the codomain. There's a lot of detail that you can look at here on the interaction between the codomain and the range of a function. I don't want to worry about that. In fact, the reason that I'm using the definition of codomain here instead of the definition of range is because I want to avoid that problem entirely. We can shorthand the definition of a function using this set of symbols. So in this particular case, we have a function named f we have a domain named curly d, and we have a codomain named curly r. Very specifically, and I'm getting a little bit ahead of myself, but very specifically, the reason that I care about codomain instead of range is I want to be able to look at a function from the real numbers to the real numbers given by, say, f of x equals x squared. You should remember from a previous class, although we'll get into this in more detail in the next video, you should remember from a previous class that the range of the squaring function f of x equals x squared is specifically the non-negative numbers, the interval from 0 to infinity. I don't want to have to worry about that. I want to be able to say, well, it's going to some of the real numbers. I don't care which ones. And that is the advantage that codomain has over range. Again, for those of you who are moving onward from this course, if you go on to study at the college, either discrete mathematics or linear algebra, in each of those courses, we take some time to investigate more carefully the relationship between codomain and range for at least a certain set of functions. So if you're going on to those courses, this is something that you can see in more depth there. For our purposes, we're not going to worry too much about the idea of the difference between codomain and range. But I do like to stress that, yeah, this is something different than the range that you're accustomed to. Because I want to emphasize that the functions that we are studying in this course take on real values and spit back out real values. For those of you who are going to go on to Calculus 3, multivariable calculus, in that course, you start generalizing exactly this idea. In multivariable calculus, you start looking at functions that go from the real numbers to three-dimensional vectors, or from three-dimensional vectors to the real numbers, or from three-dimensional vectors to other three-dimensional vectors. There's a lot of space to examine in that. Those of you who are going onward to discrete mathematics will study functions that go from the integers or go into the integers instead of the real numbers. That's the idea of discrete in the name discrete mathematics. So before we get into the functions that we're going to really be caring about, let's take a look at a function that's defined within the natural numbers. So here we have a function that's defined really on just a very small number of natural numbers. I've given this function a value for 0, which isn't actually a natural number at all, 1, 2, 3, 4, and 5. And for all the other natural numbers, this function is undefined. For any real number that is not a natural number, this function is undefined. And the values it can spit out are 1, 2, 3, 5, 7, and 11, which is a very small set of the natural numbers. But the domain of this function is the natural numbers, because that's what I defined the domain to be. The codomain of this function is the natural numbers, and the range of this function is 1, 2, 3, 5, 7, and 11. Simple name, a real valued function of one real variable. Which we often abbreviate and simply call a real valued function. Is any function going from the real numbers to the real numbers. Again, every function that we study in this course will be a real valued function of one real variable. An algebraic function is any real valued function which can be defined by a finite number of algebraic operations to the independent variable. So that includes your polynomial functions, which are described by squaring, multiplying, adding, subtracting. That also includes your rational functions, which throw some division in, and it even includes your radical functions, where you throw a square root in. Real valued functions which are not algebraic are called transcendental. Literally, transcendental means not algebraic. And you've come across some transcendental functions already. The trigonometric and inverse trigonometric functions, sine, tangent, arcsecant, all of those fun things are transcendental functions. We'll be using the trigonometric and inverse trigonometric functions in this course. You've probably also come across the exponential function e to the x and the natural log of x, or general logarithms. These are also transcendental functions. You won't see those this semester. You will see them next semester in Calc 2. The exponential and logarithmic functions are fundamental functions in a lot of different aspects of mathematics, especially my particular area of interest, which is differential equations. But we'll take this semester to build up the algebraic functions, and the trigonometric functions are plenty enough to use as examples. Let's save anything more complicated for a little bit later. When we have a function f, we can talk about the graph of f as a shorthand for saying the whole phrase, the graph of the equation y equals f of x, which, once again, something probably that you have run across in the past, because mathematicians and math teachers throughout the world are inherently lazy, and we're going to avoid talking about those sorts of things. And the last thing that I have to talk about today is the vertical line test, which, again, something you should be very familiar with. A graph represents a function if every vertical line crosses the graph at most once. And because it's very difficult to look at every single line, the vertical line test is never actually useful in that phrasing. Instead, we take what's called the contrapositive, switching things around, and say that a graph does not represent a function if at least one line crosses the graph more than once. And that's the example that I always like to give in my classes. Let's draw a quick set of coordinate axes, and let me sketch a function or a graph onto these axes that might look something like this. Is this graph a function? Well, it kind of looks like it, but I'm not entirely sure, because I know that the graph continues onward beyond the part that is actually drawn. And if the person who is trying to do this is trying to mess with us, it might be that this extension over here comes up and does a couple of loops on the way out. Or it might be the extension coming off this way comes back around like that. I don't know. There is no way for me to know if any of those things happen. If they do, then the thing we have is very definitely not a function. And that leads me to your to-do for this video. I would like you to take the time to think of a different graph other than the monstrosity that I just drew, which is not a function. And don't just draw the graph and say that it's not a function. Explain why the graph that you drew is not a function. So take a couple of minutes to sketch out that graph and write out your explanation, or draw your explanation if you prefer. And I'll see you in the next video.